Hello, my name is Tianchang, and today I'm going to present our effort on testing the robustness and operational integrity of the service-based ORAN implementations. So mobile networks transition to 5G provides support for more diverse use cases like IoT, autonomous driving, and smart factory. And the radio access network, RAN, communicates with these devices to handle their requests. And to support this more diverse traffic, 5G breaks the previously monolithic RAN into a disaggregated architecture, separating the RAN into different components, each carrying part of the network protocol stack. And this architecture allows network operators to source components from different vendors to form the RAN to cut cost. However, 5G still faces some major drawbacks. Primarily, network optimization tasks are often performed at each RAN node, which lacks a high-level view of the entire network. And to address this, Open RAN is proposed to decouple RAN hardware and the control and optimization of RAN operations. It first introduces some RAN intelligent controllers, the RIG, to control and optimize the entire network. And one primary component of RIG is the near-real-time RIG, which takes metrics from the different RAN nodes to optimize RAN operations in near real time. And different RAN nodes in this whole network can communicate with this RIG over a standardized interface defined by ORAN for interoperability. And ORAN's design promotes combining hardware from different vendors to form RAN solutions, and it also allows to use software from third parties for RAN optimization of RAN operations. And due to these advantages, ORAN are actually being deployed or trailed by major operators, for example, by AT&T and Deutsche Telekom. For a detailed look at RAN intelligent controller architecture, the E2 interface connects the RAN nodes with the RIG, and the messages and protocols on this interface are standardized by ORAN. The main function enabler of RIG are the XApps, which may perform different optimization tasks. Network operators can choose to use XApps from third-party providers to get the most optimized network. And other components in RIG support the operation of XApps, and they are running as separate programs in ORAN's service-based architecture. So each RAN node may send some reporting messages through this E2 interface to the RIG, and these messages will first reach this termination point of the E2, E2T, which it is decoded, validated, and then routed to each component or the XApps. And the XApps can then choose to send some control messages back to RAN nodes to optimize the network. However, this software-centric design in RIG and the heterogeneous nature in RAN nodes and user devices also greatly expands the attack surface of ORAN. First, in the RIG, because every component and XApp is a separate program, which are vulnerable to software bugs, misconfiguration, and dependency vulnerabilities. On the other hand, the RAN nodes can be provided by multiple vendors, connected with different user devices having drastically different traffic patterns. As such, whether due to some malicious activities or implementation flaws or just unexpected events, the RAN nodes can send unexpected traffic to the RIG. In fact, ORAN itself considers the same threat model in its study on RIG security and concludes that the near-real-time RIG should not assume that the data received is valid or trusted, and some validation should be enforced to ensure its robustness. And if the programs in the RIG are not properly protected, this unexpected inputs can lead to some severe consequences. Here you can see 4 RAN nodes having established communication with the RIG over the E2 interface. Consider due to the reasons mentioned above, one RAN node sends some malicious traffic to the RIG. And if a RIG component is not robust enough, it could lead to components crash, which these components can no longer handle any requests by other RAN nodes, leading to a denial of service of this component. Moreover, if the E2T, which is the main message decoder and router crashes, all communication channels are disrupted, and this leads to the full denial of service of the entire RIG. So in this work, we focus on finding these issues that can cause the RIG component to crash or hang due to issues like memory corruptions, which may be caused by out-of-bound memory access or no-pointer dereference. And at a high level, our goal is to test the robustness and operational integrity of ORAN RIG implementations, given this unexpected traffic that they may face. And we then design some of our design choices to solve this problem. So first, I want to touch on the limitations of existing off-the-shelf methods. Existing protocol testers like Ethernet can only handle one program at a time, so a limitation which makes them not suitable for testing RIG implementations. Because if you take this approach and test XApp1 in isolation by sending the test input directly to the XApp, first, it will require identifying the protocol and the message format details used for each component we want to test. And moreover, this internal message implementation details is not defined by ORAN specifications. So different implementations may choose to use different protocols with customized message formats. And in fact, in practice, we encounter some that are implementations using gRPC, where others may use some customized protocol. And finally, even if this isolated testing reveals some vulnerabilities, it is likely one that cannot be exploited under our threat model. Because for an input from the E2 interface to trigger this vulnerability, it has to first pass through these intermediate components, like the decoder and validation in E2T, as well as other checks by other components. And as a result, the malformed packets triggering this vulnerability may be dropped early before it can even reach the accept. And this results in most discovered vulnerabilities as unexploitable false positives under our threat model. And to solve this challenge, we instead take an end-to-end testing approach. So where we take the entire rig as a whole and sending our test inputs only through this E2 interface. And because the E2 messages are standardized and well-defined, this allows us to automate the test generation process and make it scale to different implementations. And in addition, this also ensures that all found bugs are exploitable by a misbehaving run. But this end-to-end testing approach also poses several challenges that have to be addressed. First, due to the RIG's service-based architecture, we need to generate the test inputs under the right constraint. To illustrate, in this communication chain, say we want to test this XApp. And if the input generation is under constraint, the malformed test input may be discarded early by E2T, not even reaching the target XApp. And on the other hand, consider this XApp contains 3 execution paths, but only one can lead to a vulnerability. So if the input generation is over-constrained, this path leading to the vulnerability may never be discovered by our generated test inputs because they are not diverse enough to find this path. So to address this, we instead take a layer testing approach where we first test the component directly connected with the E2 interface, which is always E2T, and then gradually move to deeper components. And when testing each component, we also collect the appropriate constraints so the test inputs can reach the next component. However, this approach requires us to understand the layer dependencies of components, and to solve this, we use some dynamic tracing during runtime of ORAN to find this information. But dynamic tracing can also miss some execution paths in each component. To demonstrate, suppose this E2T has 3 execution paths that can allow the test input to reach the exit point and to the next correct component. But the traces we collected during dynamic tracing may only cover one of these paths, resulting in missing of some potential paths and over-constraining this input generation. And to solve this, we also collect the entry and exit basic block for each input message at each component during dynamic tracing. And then we apply static analysis to find all execution paths between the entry and exit. So the next challenge lies in how to conduct this efficient static analysis that can scale to large components while avoiding the path explosion problem. Because for example, some RIG components, the implementations can contain over 6,000 functions and more than 100,000 lines of code for just a single component. And we use several techniques to address this challenge. Just briefly, first we use the program dependency graph to find the critical conditions crucial for the execution from entry to exit, which allows us to ignore paths that do not lead to the early discard of an input. And then we also try to selectively avoid analyzing complex functions responsible for generic library tasks. What I mean is, consider these 2 functions. The first one is responsible for validating and generate an input, whereas the second retrieves some UE data given a key. So we want to analyze the exact checks performed on the input, but we don't really care about the procedure for retrieving UE data. So we choose to analyze the first function, but not the second. And in practice, we use some heuristic approach to distinguish between these 2 types of functions. And our intuition is that the validation functions are typically more specific, whereas the generic library-like functions have a broader applicability and are typically invoked multiple times in different program contexts. And due to time constraints, I had to leave out a lot of technical details and other novel techniques like how we generate the automatic grammar-aware input generation. And please read our paper for more details if you're interested. But putting all our discussions together, the entire workflow of ORANalyst is divided into a pre-processing phase and a runtime testing phase. In this pre-processing phase, we use dynamic tracing to find the dependency between components, as well as the entry and exit points of a message. Then we apply the static analysis to find the input constraints we need to enforce, so the test input can reach the component under test, cut, which is the component marked in red. And the input constraint then is used for message mutator, which generates test messages based on the AS1 E2 message definition available in the technical documents. And the generated inputs are then sent to the E2 interface to the rig to test the code, with a runtime monitor responsible for collecting the code coverage feedback, as well as report any crashes caused by the test input. Now I'll share some of our evaluation results. Because there are only 2 commercially adopted and ORAN-compliant implementations available as open source projects, the ORAN software community, ORAN-SC, and SD-RAN implementations. So we evaluated ORANalyst on both implementations on their latest release to show the effectiveness. And we evaluated on 10 components across the 2 implementations, each for a 24-hour period. And we were able to uncover 19 vulnerabilities from these 6 components, as well as from some common SDKs not listed here. And 15 CVEs are assigned to track all 19 issues. And this figure shows that in ORAN's message flows, all vulnerable messages, which are messages in red, that we discovered can trigger some vulnerabilities in rig components or applications. And these issues can lead to component crashes, memory violations, or communication channel blockage, resulting in the denial of service of a single component or even the entire rig, and could lead to a potential sensitive information leakage as well. And due to time constraints, we can only demonstrate one simple vulnerability we found. So for this vulnerable code, the function online 264 performs some encoding operations on some received message fields. We found that some carefully constructed request message can lead to an encoding error in this function, leading to this value of the encoded length variable being -1. But this variable is then used as a length to initialize an array. And if the value is negative, this leads to some memory violation due to the negative size array initialization. And this is just an example of a simple problem we found. So we also conducted some comparative analysis with other state-of-the-art protocol testers, including Ethernet and BUFAS, and we found that our tool can perform the best in terms of code coverage, issues found, and the effectiveness of the generated test cases. So in conclusion, we present ORANalyst, the first testing framework for ORAN rig implementations. It combines dynamic tracing with static analysis to effectively test the operational robustness of this service-based ORAN rig. And our evaluation on ORANalyst uncovers 19 new denial of service vulnerabilities, leading to 15 CVEs assigned, and it can also outperform other state-of-the-art protocol testers in pretty much all metrics. And we open source ORANalyst at the following link. And thank you. I'm ready to take questions.